This problem is an area problem. Area problems also have two different types. There are some problems they are asking you to find the maximum area, and there are another type that you're gonna ask to find the minimum area. So let's try to understand this question. So what it says that Ryan has 60 meters of fencing materials to enclose a rectangular garden in his backyard. If one side has a pond and no need of fencing, what is the largest area he can enclose? And also find the dimensions of the enclosed garden. So they're like a very interesting question. And also you can see that this is not obvious. So what's going to happen here is, so there's a area that you want to enclose, and on one side there's a pond. So that means you don't need anything on that side. So I mean you only need to enclose three sides. But the question is, you have a lot of different options. You know, like when you want to create like a rectangular shape, there's a width and a length, and then you can pick any numbers there. The question is the total has to be 60. That's the only condition you have. The total has to be 60, and then what is the largest area that can happen? So that means you can see this is an obvious problem. So what we're trying to do is we're gonna set up an equation, and then we try to use calculus to find the maximum possible value. In this case, again, the absolute maximum that normally happens at a critical point. So let's try to do the problem. So if you get a problem like that, it's always like if you draw a figure to kind of explain the situation, it will be really helpful for you, because like sometimes those geometry problems are a little harder to understand. So the best thing that you can do is like draw this situation. So let's try to do that now. So let's draw this. So it's a rectangular garden, and then on one side there's a pond. So there's a pond on this side. So that means you don't need any fencing for that side. So we can just draw it like that. Maybe a little fish in there also. Okay, so now what we're trying to do is just try to bring mathematics here. So you're gonna pick. So what we after we draw this, what you're gonna do? You're gonna pick variables. So when you pick variables, like you're gonna think about this one. So how you do? You can see there are there's a width, that's a smaller side, and there's a length, that's a long side. So what we normally do, you look for what is common. In this case, the width is common. So for that variable, actually you're gonna pick x. These are like common things that we can do. So we're gonna pick x for that uh, most repeated one, and y for the other one. You don't have to do that, but if you do it like that, you're gonna make it, you're gonna feel a little comfortable to do the problem like that. All right, so we have that. Now let's try to bring the constraint into the problem. So what we know first is, it says that the Rhine has 16 meters of total fencing. So that means you can see the total length. So we can start the variables. So we're gonna say let. So this is how you start the problem. So let x be the width and y be the length. Y be the length of the garden. Okay, that's the starting point. So you pick the variables first. After you pick the variables, now you can write it. So we know that the total length, so the total length equals 60. So what's the total length in this one? You're going to see the total length is there's x, and then there's a y term, and then there's another x term. So which is the total, which is 60. But you can simplify this one. You can write this one as 2x plus y equals 60. So this is the constraint part. So you write the constraint. So that's the constraint. Now what we can do, we can write the objective function now. So let's write the objective function. Objective function in this case is the area. So we can say area. So which is the best letter would be A for that. So area is, we know that this is a rectangular shape. So it is the length time width. And you can see the length is y, width is x. So it is x times y. So that's what you get. And then once you write it, you will know that there are two variables here. You cannot do the problem with two variables. So what we're going to do is we're going to make it a one variable function. And how we can do that? What we're going to do, we're going to use the constraint equation to solve for y first. So from the constraint equation, you can see that if you solve for y equal, if you subtract 2x from both sides, it is 60 minus 2x. So that is the y term. Now what we can do, we can substitute that into the equation. So we can write this one as x times y was simply 60 minus 2x. So that is the equation you get. So now what we do, we can actually simplify this one. So you can write this one as, if you distribute, you get 60x minus 2x squared. That's what you get. Now we can write the actual problem. So what's the actual problem? Actual problem will be maximize. You can see maximize a, here a is a function of x, so say ax equal 60x minus 2x squared on what interval? And you can see that the smallest x, even though it is not practical, smallest x would be 0. X can be the small, this can be negative. So the smallest x would be 0. What's the largest x? So you can see in this problem, when x getting larger and larger, you can see that y is getting smaller and smaller. When you make x large and large, y get small. But what will happen is, then you're going to get a situation like this. There are two x like that, and the y is really tiny and almost 0 at the last minute. So that means, you know, to find the bound, you can see that what you can do is you can put 30 on one side, 30 on one side. That's the largest possible x you can get. So that means you're going to get 30, 0 to 30. So that is the interval that you get. So that means you need to maximize the function ax, which is 60x minus 2x squared on the interval 0 to 30. So now what we can do, we can use calculus to do that. So let's do that next. Just for future purposes, what I'm going to do, I'm going to factor 2x from this one. So if you factor 2x, you get 30 minus x. So that's what you get. So now what we're going to do, you can see that this is a parabola. It's again upside down parabola. Y upside down, you can see there's a negative a. So that means this is going to look like this. So the graph of this one going to be, so there's a 0 at 0 and there's a 0 at 30. So that means the graph going to be like that. So that's the shape of the graph. Let's make it a little bit better. So the graph going to be like this. And you can see it is 0 and 30. So we are looking for the middle point. We already know what the point is. It will be 15, but let's see how we can kind of finalize this one. So we need to find the critical point where the derivative is 0. So that's what we are looking for. So for that we can take the derivative and set it equals 0. So for critical point, we can look for the a prime x. For this one, we can use the first form, which is 60. So if you look at the derivative, you can see that you're going to get 60 and then minus 4x. Now what we do, we set this equal to 0. And then when you solve, you can see so you're going to get, this is easy to solve. So you can see 4x equals 60, and this is that x equal 15. X equal 15. So that is the critical point. So now what we can do, I'm going to use a different technique for this problem. So you know that this is a continuous function on a closed interval. You can see this is a continuous function on a closed interval. So we can use the absolute extrema test for this one. So what we're going to do, we can evaluate the function at the critical points. So let's do that. So we're going to do A15. So A15 means I'm going to use the factored form. So which is 2 times 15 times 30 minus 15. So you can see that you're going to get, 2 times 15 squared. 15 squared is 225. So you get 450. Next, what we do, we can evaluate at the endpoint. So we first evaluate at the critical point. Now next evaluate the endpoint. So endpoint, for this one we use a factored form. So you can see one endpoint is 0. So if you look at the factored form, it is 0. And the other endpoint is 30. Again, if you look at the factored form, this one, there's a factored form, you can see it is 0 again. So that means for the endpoints you get 0. It's very clear from the graph too. That's the area. So if you don't want to use the calculus, that's the other approach for that. Okay, now we can clearly see that the maxima happen at that point. So because of the absolute extrema test, that is the maximum value. Okay, so from from the absolute extrema test. What's the absolute extrema test? You evaluate the function of the critical points, you evaluate the function of the 8 points, pick the largest. That's the absolute extrema test. So yes, it's the absolute max. Okay, it's very clear. From the absolute extrema test, the largest possible area is 450. Whatever the unit here, since it was feet, so it's feet squared. So that's the largest possible area Ryan can get for this pond. Mathematics says that, and there's no way you can go more than that. Okay, and then the dimensions are, you can say when you remember y was y. So what was the y? Y was 2 minus y was 60 actually. 60 minus 2x. So that means when x equals 15, you get 60 minus 30. So which is 30. So y is 30. So x equals 15, y equals 30. And you can say the possible area is 450 when you're going to say the width. We don't say x. Width when the width is 15 feet and the length is 30 feet. So that's how you kind of complete the problems. You have to write the line at the end just to, because you have to answer the question. If you don't answer the question, you are like half done. Okay, so that's how you do the problem. So in this case, actually, we didn't use the first derivative test or the second derivative test. You don't have to, because we use the absolute extrema test for this problem. That's like another way to do a problem. But you are welcome to use the other techniques as well. So in another problem, we try to use the first derivative test. Okay, so thank you.